We will review writing and balancing a chemical equation, predicting products in a chemical reaction, predicting solubility of a compound, 3 different types of reactions, spectator ions, and calculating oxidation number, and how to represent a chemical reaction using a balanced chemical equation and net ionic equation. So let us go ahead and see. When sodium chloride and silver nitrate mixed, there is a white precipitate formed in the beaker. So which are the ions responsible for that reaction? That is, only silver ion combines with a chloride ion. This is from sodium chloride, but it doesn't matter. It can be from KCl. And this is from AgNO3, but it doesn't matter. Any Ag ion, silver compound can be combined, that is soluble in water, can be combined in order to get AgCl. So in a complete equation, normal balanced chemical equation, we will write if it is NaCl plus AgNO3, we will get N-to-N combination and this combination, right? Center to center. So NaNO3 we will get and AgCl we will get. This is the complete equation. This shows that, okay, these are the two chemicals I mixed and I got AgCl as solid. That is the reason for the chemical change. This is the equation for that whole reaction. But depends on the details the chemist need. He needs to know or she needs to know only which are the ions responsible for that chemical change. So that is what is the net ionic equation. So irrespective of the source, the chemist can form this product. So that is what is simplified by the net ionic equation. So what is the final equation for that product formation? Okay, so that is what is net ionic equation is. That is why it is important. There are 3 major types of chemical reactions in aqueous solution, which are, first one, as we have just seen, precipitation reaction, right? That is the one we have seen. And another one is acid-base reaction. Acid-base reactions are the reaction between an acid and a base. And the third type of aqueous reactions are redox reaction. One of the reactant is getting oxidized and the other one is getting reduced. So oxidation, reduction reaction or redox reaction. So these are the 3 types of aqueous reactions that we have to learn how to write net ionic equations. So let us see with an example how to write net ionic equation. Normally we follow these 3 steps. Okay, so we will first write a complete molecular equation, which is our regular balanced chemical equation. So for the previous example, when we combine sodium chloride, which is dissolved in water, so we will write AQ in parenthesis, which combine with the silver nitrate, which is also soluble in water. So we will write AQ in parenthesis. AQ means aqueous. So then we are getting the product N-to-N combination. So that is first NaNO3, which is going to be soluble in water. And then Ag and center to center, Ag and Cl, always write the positive ion first. So that is why we are not going from this side to this side. So AgCl, which is a solid. I will explain how to decide which one is aqueous, which one is solid using the solubility rule chart, which will be discussed in the next slide, upcoming slide. Okay, so after writing the molecular equation, we will write a net ionic equation. So complete ionic equation. So we call it as molecular equation. And the complete ionic equation is like this. For the complete ionic, we will write the ions when sodium chloride is dissolved in water. We have seen sodium ions will form, chloride ions will form. And silver nitrate also will dissociate into silver ions and nitrate ions. Okay, and then on the product side, again, we will have sodium ion and NO3 ions and AgCl is a solid. Solid will not be in the ionic form, so it is going to be solid as such. We will write. Okay, so in the liquid, all the ions floating around are sodium ions are there, chloride ions are there, NO3 ions are there, correct? And Ag ions are there. All these are floating around except AgCl, which will be the solid at the bottom. Okay, so that is the picture of it. And then cross out the spectator ion. What are spectator ions? Spectator ions are the ions that appear on both sides of the arrow mark. So I can see when I rewrite this one to show you the spectator ion, I can see the sodium ions are same on both sides, NO3 ions are same on the both sides. So what I will do, just cross that one out. So Na plus is here, Na plus is here, and I have NO3 minus, NO3 minus. What are the things left on the left side? We have two ions. On the right side, we have a compound. Okay, so that is the one we are going to write it down here. So that is, we have Ag plus and Cl minus on the left side of the arrow mark, and on the right side we have AgCl solid. So this is called the net ionic equation, or this is the complete ionic equation. Okay, so these are the three steps we are following when we write the net ionic equation. While writing the net ionic equation, you should know two more things. Which one will ionize, which compound will ionize, and how to determine the solubility and write the state symbol of that compound. Solids, gases, and pure liquids are not going to ionize, and weak acids are also not going to ionize. So whenever you see S in parenthesis, do not ionize that compound. Whenever you see G in parenthesis, do not ionize, and L, do not ionize, and weak acids will not ionize. Okay, so these points you should remember while writing net ionic equations. Here is an example chart for the solubility rules. You may have a different one in your reference material, but in basically how to read that one is compounds contains lithium ions, sodium ions, potassium ions, and ammonium ions are always soluble. Okay, always soluble. There are no exceptions for these ions. Say for example, if you are putting an ABr, K2SO4, ammonium carbonate, all these salts are going to be soluble in water. And another example, let us take NO3 minus and acetate ions, always soluble. Okay, there are no exceptions here either. So let us see another example here, chloride, bromide, and iodide. These are mostly soluble, not always soluble. There are some exceptions. We have already seen AgCl is insoluble, and in the example we are discussing now, the lead iodide is insoluble, right? So that is how it is going to be helpful. The solubility chart is going to be helpful for you to decide, okay, which salt is going to be insoluble, which salt is going to be soluble in water. So you can always refer to this one, all right? Now you can try writing a net ionic equation for the reaction between sodium sulfate and barium chloride and check your answer. You must have these equations in front of you now. The molecular equation Na2SO4 plus BaCl2 gives you 2NaCl plus BaSO4. That is the balanced chemical equation. So then you must be having the complete ionic equation, 2Na plus because there is a subscript 2 here, and then SO4 2 minus, and Ba2 plus because barium is charge is 2 positive, and there are 2 chlorine, so 2 Cl minus, right? And then here 2 coefficients, so that 2 goes for Na as well as Cl, so 2 Na plus and 2 Cl minus. And then BaSO4 solid, we cannot split into ions. So you must be having the spectator ion crossed out, and you have the net ionic that looks like this, right? Good job. Let's see another example. Write net ionic equation between sodium hydroxide and hydrochloric acid. So it is very clear that it is written hydroxide, so that's a base. And it is written hydrochloric acid, so that is an acid. So this is a reaction between acid and base, so which is acid-base reaction. You will get salt plus water. That means acid is getting neutralized by base. So we are going to write the neutralization reaction for sodium hydroxide and hydrochloric acid. So let us see how to write the net ionic equation for this reaction. This is a particle representation of neutralization reaction we just discussed. HCl is the particle diagram here, and NaOH, when it combined, we will get water and sodium chloride. Okay, so now how to write the complete molecular equation, balanced equation. Let's see. So HCl, the state of matter AQ, which is dissolved in water, AQ with NaOH gives you NaCl AQ and water, pure liquid. So this is our molecular equation, which is already balanced. You can see that. And now let us write the complete ionic equation. So it is going to split because it is a strong acid. So H plus, Cl minus, Na plus, OH minus, and Na plus and Cl minus on the right side as product side, and water we cannot split because it is pure liquid. And now we can see the spectator ions on both sides, which is looking same on both sides, Na plus, Cl minus, and Cl minus. We are going to take those spectator ions off and we are going to write our net ionic equation. H plus plus OH minus gives you H2O liquid. That is the net ionic equation for a strong acid combines with a strong base. Okay, here the reaction between zinc and copper sulfate. So let us write that equation first. Zinc is Zn. It is not a compound, so definitely that is solid. That's a metal, correct? Plus copper sulfate. So CuSO4, which is aqueous, which is dissolved in water. So you will get, it's a single displacement reaction, oxidation reduction reaction, right? So here Zn combines with the SO4 because Zn is more reactive than copper in the reactivity series. So we will get the product ZnSO4, which is Aq, can be soluble in water, copper, which is solid. So then we will write Zn is solid, so we have to just write as such that one, and copper will be ionic form, SO4 will be ionic form, will give you Zn ionic form, SO4 ionic form, and copper in the solid form. So do we have a spectator ion here? Yes, I can see SO4 minus 2, SO4 2 minus, it doesn't matter 2 minus or minus 2, it can, right? Either way. So both are cancelled out, right? So we will write the net ionic now. How can we write the net ionic is Zn solid plus Cu 2 plus gives Cn plus 2 plus Cu solid. You can see that this is an oxidation reduction reaction very clearly because Zn oxidation number is 0, Zn here it is plus 2, so that means oxidation number increases, so this is oxidation. And for copper, it reduced to 0. 2 plus changes to 0. That means that is reduction. That is why it is called redox reaction. And this is the net ionic equation for a redox reaction. So only thing is in the reactivity series, you have to look whether it is going to react or not based on this reactivity. Only more reactive metal can displace the less reactive metal from its solution. Okay, so let us practice some questions how to find the oxidation number of each element here. So the first one, let's go ahead and do for K2Cr2O7. So we have to find for potassium, we have to find for chromium, and also we have to find for oxygen. So oxygen is the easiest one and potassium is the easiest one. It's not going to change, and it is not peroxide. So we know for oxygen it is -2. Chromium is transition metal, so we have to calculate for that one. So for potassium, it is going to be +1. And how many potassium we have here? We have 2 potassium. So it will be 2. And chromium, I don't know. So I will just put X. And we have 2 chromium. Okay. So that equals 2X. And for each oxygen, I have -2. And how many oxygen I have? 7. So that will total -14. So we have to add them up. Remember, the sum should equal 0 because this is a neutral compound. When I take the sum, how much is that going to be? 2 plus 2x minus 14 should equal 0. So then I can simplify this one to find what x is going to be. So 14 minus 2, and x is going to be 12 divided by 2, that equals 6. So now I know for chromium it is +6. Each chromium is +6. Each oxygen is -2 and potassium is +1. Okay. And now let us take the second example. This one's carbonate ion CO3 2 minus. So let us find for carbon. We don't know for carbon. I have one carbon, so I will just put X, that equal 1X. And then oxygen. Each oxygen is -2. I have 3 of them. So that means -6. So when I add them up, 1x minus 6 should equal the charge of the ion here, which is -2. So x equal 6 minus 2, that equal 4. So for carbon, I have 4, and for oxygen, it is. So carbon, it is +4, and oxygen, it is -2. That's the answer for this. And now for MnO2. Let us try for MnO2. Okay, so let us try for Mn. I don't know. So Mn, I can actually simplify now. You know the method. So I will just write X plus I have 2 oxygen. Each oxygen is -2. This is a neutral compound, that equals 0. So X minus 4 equals 0. So X equals 4. That's how I can do. The next one is PCl5. Let us calculate for phosphorus. So X plus I have 5 chlorine. Each chlorine is -1. That should equal 0 because that's a neutral compound. X minus 5 equals 0. So X equals 5. Alright. And now the last one, SF4. How to do that one? X plus fluorine is -1. So 4 times -1 should equal 0. So x minus 4 equals 0. So x equals 4. Okay, that's how we can calculate the oxidation numbers. And now try these equations, complete the equation, and classify and balance it. Okay, and check your answer in the next slide. You can pause it and try to do it by yourself and check your answer in the next slide. Here you can see the answers, and please check and see whether you are getting it or not. And yeah, so practice more questions and equations, and how to write the product is important, and the state of matter, how to write AQ, when to write S, when is it going to be precipitation reaction. All these are very important when you go into the net ionic equation. Okay, so I hope you have an understanding of the types of reaction now. And now let us review some calculations.
Solid copper 1 sulfide reacts with oxygen gas to form copper 1 oxide and sulfur dioxide gas. How many grams of copper 1 oxide will be formed from the reaction of 75 grams of copper 1 sulfide and 21.5 grams of oxygen? If 55.8 grams of copper 1 oxide are produced, what is the percentage yield? So two questions here. So first what we will do is, since we have the word reaction given, we have to write the symbol equation first, and we have to balance it. So copper 1 sulfide. So copper 1 sulfide is Cu2S. Sulfur is -2, copper is +1. So we will have Cu2S. that reacts with oxygen, and this is solid, this is gas, and we will have copper oxide, that is solid, plus sulfur dioxide gas. And now when you balance it, we can see 2 and 2 and 2 here and 3 here. And now from the equation, so from the question we have 75.0 grams of copper 1 sulfide and 21.5 grams of oxygen, and it also says we have 55.8 grams are produced, that is copper oxide are produced in the lab. That is going to be our actual yield. Okay, and now what we have to do is, since we have the information for both reactants, we have to find which one is the limiting reagent. So the limiting reagent I'm going to find for Cu2S, that's a reactant, and I will see how much Cu2O will form. Okay. For that one, I will start with what is given. So I have 75 grams of Cu2S and divide by 1, and I will convert that mass into moles. So we know in 1 mole of Cu2S we have 159.152 grams of Cu2S. So first I have to convert it into moles, and then I can convert that moles to the ratio of moles in the equation. That's the mole ratio between copper 1 sulfide and copper 1 oxide is 2 moles of copper 1 sulfide. The mole ratio is 2 moles of copper 1 oxide. So how much is that going to be? The grams of copper 1 sulfide, grams of copper 1 sulfide cancels, moles of copper 1 sulfide, moles of copper 1 sulfide cancels, and we will have moles of copper 1 oxide. So we can have the numbers from the numerator 75 times 2 moles of copper 1 oxide divided by 159.152 times 2. So 2 we can cancel, and 75 divided by 159.152 equals 0.47 moles of copper 1 oxide. And then we will see the other reactant oxygen, how much copper oxide it will produce. Okay, so for that one I have 21.5 grams of oxygen given divided by 1, and I can convert that one into moles. So we know in 1 mole of oxygen, the molar mass of oxygen is going to be 31.98 grams of oxygen, right? And then that moles of oxygen, I will compare the stoichiometric relation, the mole ratio in the balanced chemical equation. So 3 moles of oxygen, 2 moles of copper 1 oxide. Now I can cancel grams of oxygen, moles of oxygen, moles of oxygen. I will have moles of copper 1 oxide. So I have the numbers that equal 21.5 times 2 moles of copper 1 oxide divided by 31.98 times 3 in the denominator, that equal 43 in the numerator, 95.94 in the denominator, that equals 0.45 moles of copper 1 oxide. So which one is the lowest number of moles here is 0.45 moles of copper oxide. So we got that one using oxygen. So oxygen is the limiting reagent. Okay, and then we can find the second part, that is, okay, they're asking the mass of copper 1 oxide. So mass of copper 1 oxide equal moles of copper 1 oxide times molar mass of copper 1 oxide. So that equals, now we can say that 0.45 moles of copper 1 oxide equal, in 1 mole of copper 1 oxide we have 143.09 grams of copper 1 oxide, that equals 64.39 grams of copper 1 oxide. And now we can find the percentage yield. So the percentage yield equal actual yield divided by theoretical yield times 100. So that equal 55.8 divided by 64.39 times 100. So that will be 86.65 percentage. Alright, so now we can see the cross multiplication method. So first we can write the equation. So that is 2C2S plus 3O2 gives you 2Cu2O plus 2SO2. And then we have 75 grams of copper, 1 sulfide. So I will write 75 under Cu2S. And we have 21.5 grams of oxygen. So I will write 21.5 grams under oxygen. And now first I will go with the copper 1 sulfide, and I will see how much copper 1 oxide will form. So I will find the number of moles by dividing with the molar mass of copper 1 sulfide, and I will get 0.47 moles. So now I can see the mole ratio, that is 0.47 moles will give how much copper 1 oxide. So I know from the balanced equation 2 moles, because here too 2 moles of copper 1 sulfide will give me 2 moles of copper 1 oxide, 1 to 1 ratio, correct? So how many moles of copper oxide will form from 0.47 moles is the same number of moles. So that means I will have 0.47 moles. Okay, so that's what going to be the number of moles of copper 1 oxide from copper 1 sulfide. And now I will see from oxygen how many moles will form. So then 21.5 is the mass of oxygen divided by the molar mass of oxygen is 31.98, that equal 0.67 moles I am getting. And now from the balanced equation I have 3 moles of oxygen, and that gives 2 moles of copper 1 oxide. Okay, so how many moles will form from 0.69? 0.69, how many moles? So what I will do, just cross multiply, right? So the number is 0.67 times 2 divided by 3, that will give me 0.45 moles of copper 1 oxide. So when you compare this one, that is from copper 1 sulfide, and compare the moles formed from oxygen, the number of moles of copper 1 oxide formed from oxygen is less than number of moles of copper 1 oxide formed from copper 1 sulfide. So this oxygen is the limiting reagent. To find the mass of copper 1 oxide formed, we will just multiply the number of moles with the molar mass. So number of moles we have to take for the limiting reagent now. So because that decides how much product it will form. So 0.45 times the molar mass of copper 1 oxide is 143.09, that equal 64.1 gram of copper 1 oxide. So that's the mass. And now we can find the percentage yield using the formula actual yield divided by theoretical yield times
64.39, that is grams of copper 1 oxide formed or calculated. Okay, and then we can calculate percentage yield, actual yield divided by theoretical yield times 100, that equals 55.8 divided by 64.39, that equals 86.65%. To analyze the alcohol content of a certain wine, a chemist needs 1 liter of an aqueous 0.2 molar potassium dichromate solution. How much solid potassium dichromate must be weighed to make this solution? Let's see. What are the things given? List them out. Volume is given, molarity is given. They're asking us to calculate the mass. Use the formula molarity equal moles of solute divided by liters of solution. And then moles expand mass over molar mass. And then substitute. And then you can find the mass. So first what we will do, with the given molarity and the volume, we will calculate the number of moles. And then from the moles, what we will do, we will calculate the mass by multiplying moles and molar mass. And the unit will be in grams. Now a dilution question. What volume of 16 molar sulfuric acid must be used to prepare 1.5 liter of a 0.01 molar sulfuric acid solution? So what is given? Let's see. We have molarity of the first solution, that is 16 molar, and V2 1.5 liter, that is what we need, and we need the concentration 0.01 molar. Okay, so what is unknown here is the volume 1, which is how much concentrated sulfuric acid we have to take in order to prepare 1.5 liter of 0.1 molar solution. So which formula we have to use is M1V1 equal M2V2. Okay, so M1 is the molarity of the first solution, volume times volume of the first solution equal molarity of the second solution times volume of the second solution. So we will just substitute. So M1 is 16 molar times V1, that's what we have to calculate. And then M2 is 0.01 and V2 is 1.5 liters. So when you solve it, we will get 0.00094 liter. And if you convert it into milliliters, it will be 0.94 milliliter. You do not have to convert it into milliliters here because the volume, what is given in the question is in liters. So we have to just keep it like in liters. So that's how we can solve a dilution question.